Find the volume of the solid formed by revolving the region bounded by the graphs y equals the square root of x and y equals x squared about the x-axis. So notice that in this particular example, like we don't have an interval over which we are integrating like we did in some of the other ones. So this is sort of like those area ones. And remember that whenever they don't give you an interval, that usually indicates that the two graphs intersect each other. So you'll have to find those points of intersection to find the bounds of your integration. Let's start by drawing a picture. Yep, sounds like a good idea. So here we go. We've got the square root of x. We have, so here's the square root of x. Ta-da. Wow, that's probably the best square root of x graph I've ever drawn. Right, and then we have basically its inverse right there. That one is less spectacular, but you know, you do what you do. All right, you do what you can do. So we have that shape, that plane region. We're going to take that thing, we're going to revolve this around the x-axis. Let's sketch in a representative rectangle thusly. Go away. Right. All right, since we have a vertical rectangle because it's perpendicular to our horizontal axis of revolution, that means our height is going to be delta x, and by height, you know, it's the width of that rectangle, of course. And then as I did in some of those, in that other video here, I think it's a little bit easier to visualize if I draw this thing over here. So here is the little rectangle that I am revolving around. And then turn this thing into a disk. Wait. You have forgotten. So you reflect a little piece here. Does that look about symmetric? Okay, this one does, and then maybe right about there. Okay, yeah, that's good. Right, so let's say, I'm going to actually draw this in this direction this time. So here is the whole part. Oh, I like this better. It looks even better than before. Okay, that's very nice. All right, and then you can visualize the bottom side of that on the back side. I'm not going to draw it. Okay, so you need a couple of pieces of information. We already said that the height of this washer is going to be delta x, but we also need two radius lengths. Here's the outer radius. Let me come back over here to this picture, and I'm going to draw that outer radius. So I can see that it is the distance from the x-axis up to this blue function, and that's the square root of x function. So this outer one is the square root of x. And then the inner one here, this inner radius, again, once again, I'm going to draw this in here. That's this distance from the x-axis up to the green function, and that green function is x squared. So that's the inner radius, x squared. All right, I think that we are ready. We have all the stuff that we need in order to find the volume of this. Volume should still be equal to a pi, definite integral from, what's our, well, I know 0 is one of them, and then I have to set these equations equal to each other in order to solve. I already know it's 1, but you know, I'll just go through the motion. So I square both sides, I get x is equal to x to the 4th, and let's say subtract that thing over 0 is equal to x to the 4th minus x. Factor out an x to the 3rd minus 1. Yeah? Yeah. All right, so our first solution, x is equal to 0. Well, we already knew that one. And then we have x squared, x cubed minus 1 is equal to 0. X cubed is equal to 1, so x is equal to 1. Right? Not plus or minus because it's odd. There you go. So there's our bounds integration, of course. Like you said, I mean, you could have guessed it. They're inverses of each other. Okay. All right. So inside the integral, we will do outer radius, which is being squared. So the square root of x squared minus the inner radius squared, x squared, and then with respect to x. All right, we have set up our integral. Now it's time to just do the calculus that is necessary to solve this thing. So this is, when I square this, that'll just be x. When I square this, will be x to the 4th. Antiderivative, x squared over 2 minus x to the 5th over 5, evaluated from 0 to 1. Plug in your 1, pretend like you're plugging in the 0, and then I would get pi times 1/2 minus 1/5. Common denominator there is a 10. That'll be a 5 minus a 2 up there, which is 3 pi over 10 units cubed. For our volume, let's go ahead and take a look at, before we conclude this thing, what all of this is supposed to look like. So there is a professional picture of this whole deal. It looks pretty much exactly like I drew it. And then here is a professional rendering of what this three-dimensional solid looks like.